Welcome, everyone. Ready to dive towards deep learning models resistant to adversarial attacks. This paper is a real cornerstone for understanding how to build models that can handle those tricky adversarial attacks.
Absolutely. And knowing your expertise, we can skip the intro stuff and get right to the core. Authors bring in a new angle using robust optimization, specifically a saddle point formulation, to make models that can stand up to these attacks.
Yeah, it's not just about making a model that's good at its main job. It's got to hold up when it hits those carefully crafted, practically invisible changes.
Exactly. The paper tackles this by kind of framing it like a game between two players. You got the attacker searching for the model's weak points, and the defender trying to make the model tough as nails. That's where the saddle point formulation comes into play.
Okay, walk me through that. How do these two players actually work mathematically?
Boils down to two optimization problems working against each other. On one side, you've got the attacker trying to find the best change to maximize the model's loss. That's the inner maximization problem. On the other side, we're trying to train a classifier that minimizes the loss, even with those worst-case changes. That's the outer minimization problem.
Okay, I see how that sets up this adversarial training. But how do we find those adversarial examples to train against? It seems computationally tough.
And that's where the paper gets really interesting. They found that projected gradient descent, PGD, is surprisingly good at creating these adversarial examples. Consistently finds those attack points that cause a high loss.
So PGDs are attackers' secret weapon.
You could say that. Experiments showed PGD always finds these points of high loss, these local maxima, meaning it's a super effective way to make those worst-case changes.
So it's not just about finding any adversarial example. It's got to be the most effective ones to train against.
Yeah.
Guessing this has implications for the whole first-order adversaries family.
Exactly. The effectiveness of PGD tells us these first-order adversaries, which rely on local gradient information, are a real threat. It's a benchmark for the attacks we need to defend against. If a model can handle PGD attacks, it's probably going to be stronger against other first-order attacks, too.
Makes sense. But training models to be robust to these attacks can't be easy. The paper talks about network capacity. Can you explain that?
Experiments showed a key thing. Bigger networks are just better at resisting these attacks. Think about it. A strong decision boundary needs to be more complex, more nuanced, to handle these adversarial nudges. That complexity needs bigger network capacity.
So not just about classifying the clean data right. It's about making a model that can navigate this whole tricky landscape of attacks.
You got it. It's about building a model that generalizes well, even in those adversarial conditions. The paper looked at different training types, standard, FGSM, and PGD, and found that training with PGD, where the model's constantly challenged by those universal adversaries, makes the most robust models consistently.
So PGD is not just good at finding attacks. It's crucial for training robust models, like really pushing the model to its limits during training so it's ready for anything in the real world.
Great analogy. The results they got on MNEST and CFAR10 really show how well this works. The models trained against PGD were way more robust compared to those trained using standard methods or even FGSM.
Okay, so we know training with strong adversaries, like PGD, is key for robust models. What about the theory behind it all? Doesn't the paper dig into how we can use those adversarial gradients during training?
You're right. That's where Danskin's theorem comes in. Now, before we get too deep into that...
Hold on, let's pause here. We've covered a ton already. Good spot to take a breather, let everyone process this. We'll pick up right where we left off in the next part, where we'll unpack Danskin's theorem and its role in adversarial training. Stay tuned.
So yeah, Danskin's theorem, it kind of gives us the theoretical okay to use those adversarial gradients when we're training. It's a bit complex, but basically it tells us that using the gradient at those adversarial examples, the direction of steepest descent, it's a legit way to update the model's parameters.
So it's like Danskin's theorem is our mathematical proof, saying this whole adversarial training thing is solid.
Yeah, exactly. Gives us that theoretical confidence to go ahead and train models using those adversarial examples, knowing mathematically we're on the right track.
That's good to know. But the paper doesn't stop at just outbounded attacks, right? They looked at outbounded attacks too. What's the difference there?
You got it. They dug into those in the appendix. Abounded attacks, they limit each feature perturbation by itself, while almost bounded attacks, they constrain the total magnitude of the perturbation. Kind of like different ways to limit how much the attacker can change those adversarial examples.
So like with ABOD, they can tweak each feature a bit, but with ADD, they have a limited total change they can make across all the features.
That's a good way to think about it. And what's interesting is they found that PGD, even though it's a beast for A-bounded attacks, It wasn't as dominant with the two-bounded ones.
So our universal first-order adversary, not so universal after all.
Well, it's still super effective, but it shows us that different attack strategies might be needed for different types of constraints. Actually, for those A2-bounded attacks, they used a decision-based attack to really expose the model's weaknesses.
Makes sense. Different constraints, different tools, right? It's this constant back and forth between attack and defense. Speaking of which, that transferability idea, that was really interesting. Can you tell me more about that?
Transferability, it's this cool thing where an adversarial example made for one model can trick a totally different model, even if they have completely different architectures.
Wait, so our little gremlin could reuse those stickers on a different stop sign. That's kind of risky.
It is, yeah. It shows a potential weak point. But there's some good news about transferability in the paper. Remember how we talked about network capacity and using tough adversaries during training?
Yeah, those were our key ingredients for making robust models. More capacity, stronger training partners.
Right, well, it turns out those same things also make it tougher for adversarial examples to transfer. When we train against strong adversaries like PGD and use big networks, we're basically forcing the model to learn features that are more robust and generalize better, which makes those transferable attacks less effective.
So it's like those robust features become so specific to the model that those generic sticker attacks, they just don't work as well.
Exactly. And the paper showed this reduced transferability. You can see it visually in Figure 8 and in the numbers in tables 3 and 4. The models trained with PGD and higher capacity, they were much less vulnerable to attacks transferred from other models.
So making those robust models not only makes them strong against direct attacks, but also against those sneaky transferable ones.
Win-win, right. You got it. Means focusing on robustness has multiple advantages. Leads to models that are safer and generalize better overall.
This whole transferability discussion, it brings up a really interesting question. Could we get to a point where transferability is basically impossible? Where those adversarial examples are so specific, they just don't work on any other model?
Now, that's a great question. And it opens up some exciting avenues for more research. The paper showed that increasing robustness makes transferability less likely. But getting to complete non-transferability, that's a challenge still out there.
Makes you wonder if there's like a fundamental limit to transferability. Or if we could, in theory, create models that are so unique, so strong, that those transferable attacks just wouldn't work at all.
It's a really interesting thought, almost like a philosophical question about what generalization really is and what it means for a model to really understand the data.
We've gone through a lot in this deep dive, explored all those details of adversarial attacks, robust optimization, and transferability. Building robust models is a complex challenge, that's for sure, with both practical and theoretical stuff to think about. But before we finish up, let's make sure we highlight those key takeaways. What are the most important things for everyone to remember?
Good point. Let's go over the main points. Okay, so the main takeaways. First, we got to recognize that these adversarial examples are a big deal. They can fool even the smartest deep learning models, shows a real vulnerability in how they learn and generalize.
Right. It's like a reminder. We can't just focus on how well the model does on clean data. We need to build in robustness from the beginning.
And that's where the paper's idea of robust optimization comes in. It gives us a structured way to approach building models that can handle these attacks. It's like we're giving them the tools and the training to expect and block those adversarial hits.
And one of the most important tools is PDD projected gradient descent. Turned out to be really good at both finding those weak points and training the models to be tough against them.
Yeah, it shows how important it is to train against tough adversaries, really push those models to their limits so they're ready for anything they might see in the real world.
And we saw how network capacity is crucial. Bigger networks with more power are just better at learning those complex decision boundaries that can deal with these adversarial nudges.
It's like giving the model a bigger space to work in so it can build a more detailed and stronger picture of the data.
And the foundation for all of this is Danskin's theorem. That theorem gives us the mathematical proof that using those adversarial gradients during training is a valid and effective way to make things more robust.
It's like having a math blueprint showing us how to get to those stronger solutions.
But it doesn't stop there. Remember, we talked about transferability, where those adversarial stickers we make for one model might actually work on another one.
Transferability is definitely a worry, but the paper gave us some hope. It turns out those same things that make models robust, the high capacity, and training against strong adversaries also make them less vulnerable to those transferable attacks.
So it's like those robust features become so ingrained in the model, so unique, that those general transferable attacks just don't hit as hard.
Exactly. And it raises some really interesting questions for the future. Can we make models so robust, so unique, that transferability is basically impossible?
That's a cool thought. It really makes us rethink what it means for a model to really generalize, to truly understand the core concepts.
This deep dive has given you the foundation, the important concepts, and tools to explore these questions more. The field of adversarial machine learning is changing so fast, with new attacks and defenses coming out all the time.
It's a constant back and forth, but with every discovery, with each new thing we learn, we get closer to building AI systems that are truly robust and dependable systems that can handle not just the challenges we expect, but the ones we don't even see coming yet.
So keep asking those hard questions. Keep pushing the limits of what's possible. You never know. You might be the one to make the next big breakthrough in this exciting field.
It's been great diving into this with you, and we hope you, our listeners, found it useful and interesting too. Until next time, stay curious and keep those algorithms strong.